Alright, so we want to find the equation this time, and this time the graph's given to us, so we need to take a look at this graph and compare it to a standard graph of y equals sine of x and see what has changed. So we're trying to compare this to a normal sine and cosine function. So in general form standard, this is what sine and cosine functions look like. Y equals a sine b x minus c plus d, or y equals a cosine b x minus c plus d. So really, if we want to write a sine equation, we need four parameters. We need to know what a, b, c, and d are: the amplitude, the period, the phase shift, and vertical displacement, so we can write it as a sine function. So one piece at a time, we're going to try and come up with that information from the graph given to us. So I'm going to start off by drawing a midline on this graph. The midline is going to give me one crucial piece of information. The midline is going to help me determine what the amplitude and what the phase shift are. Sorry, what the vertical displacement and the amplitude are. So here I've drawn a midline. Alright, so this is called a midline. I should change the color of that one so it's a bit more visible. Let's make it purple. Midline. You'll notice that the midline is at y equals -3. So what information can we determine from that fact, that the midline is at y equals -3? It's telling you that the graph has moved down 3 units, because the midline is supposed to be at y equals 0. If you look at a normal sine function, a normal sine function will look like this, right? Y equals 0 would be the midline. However, our midline is at y equals -3. So what this is telling us, it's telling us that our vertical displacement d is -3. Right, so the first step that I did is I drew the midline. So draw the midline. Therefore, we know that the d value is -3. What else can we figure out by looking at that midline now? We can figure out what the amplitude is. What would the amplitude be? 2.5. If you count the distance from here to here, that's the amplitude. We can also calculate the amplitude using the formula that was mentioned in previous day's notes. Amplitude is absolute value of max minus min divided by 2. So that would have been, the max value is -0.5 minus the minimum value is -6.5 5.5 divided by 2 and the absolute value of that. So that would work out to 5 divided by 2, which is 2.5. Right? So same idea there. You can use the formula, or you can just look at the graph. One or the other, whichever works for you. So we got two pieces of information. The next piece of information that we need is the b value. Now for the b value, we have to sort of do the opposite of the period formula. You would have realized that the period of the function is 2 pi divided by b. Right? Whatever the normal period is, apply to that any horizontal expansion or compression. If it's horizontal expansion, the period is going to increase. If it's horizontal compression, the period is going to decrease. If I rearrange that, I can also get that b is going to equal 2 pi divided by the period. If I interchange those two variables, cross multiply. So I'm going to find the b value by using that formula. Take 2 pi divided by the period. The period I can actually tell just by looking at the graph. I just need to find 2 points that repeat themselves. So points where the graph is repeating itself, and then count the distance. So let's say I want to use this point and this point. This is the period of that graph. It starts repeating after those many points. So let's see what the period ends up being here. How much is each box worth? If 2 boxes are pi over 4, each box is going to be worth pi over, not pi over 2, pi over 8. It's half of pi over 4, so pi over 8. And the period is 4 boxes of pi over 8. So 1, 2, 3, 4. So 4 pi over 8, which is the same as pi over 2. Right? Pi over 2. So the b value as a result is going to be 2 pi divided by pi over 2, which is the same as 2 pi times 2 over pi, which is 4. So the b value ends up being 4. Okay, those things are really easy to figure out. The trickiest part is figuring out the phase shift, right? How much the graph has moved left or right. So for the phase shift, I actually have multiple choices. You'll again notice that a normal sine curve starts at 0, 0. Right? It's starting at the center, at the midline. In our case, our graph is going to start at the midline and left or right a bit. So I can say the sine function could have started right here. This could have been the starting of y equals sine of x. Right? Or it could start right here. Or it could start right here, depending on where you want to look at it. And depending on what the starting point is, you're going to get a different phase shift. Right? So the phase shift could actually be pi over 8 units left. Or it could be 3 pi over 8 right. Or it could actually be 7 pi over 8 right. Right, and so on and so forth. I can use any one of those phase shifts. So here are some of the different equations that will satisfy this graph. The 3 aspects are going to remain the same. The a, the b, and the d value is going to remain the same. Only thing that can change is the phase shift. So one of the equations for this graph would look something like this. Y equals, the a value is 2.5, sine, b value is 4, brackets, x, pi over 8 units to the left, so x plus pi over 8, and then minus 3. I could also have written y equals 2.5 sine 4 x 3 pi over 8 units to the right, so x minus 3 pi over 8 minus 3. Since a sine function starts at 0, goes up to the maximum, then down again, I can also write the equation as a negative sine function. Negative sine function would just mean there's a reflection in the x-axis. The sine function has gotten flipped, right, upside down. So if I look at a negative sine function would look something like this. It would just be flipped, right? That would be the negative sine function. It's been reflected along the x-axis. So I can write the equation also as a negative sine function. A negative sine function would actually start from here. This would be the starting for a negative sine function. Starting at 0, it's going downwards and then coming back up again. A negative sine function could start right here. Right? A negative sine function could start right here. A sine function starting at 0 or the midline and going up. a negative sine function starting at 0 or midline and coming down in the opposite direction. So one of the equations I could have written as a negative sine function is I could have written as, I'll just move this part over. Put that over here. So negative sine function, I could have written that as y equals negative 2.5 sine 4x. The negative sine function would start from pi over 8 to the right. So minus pi over 8 minus 3. Right, so only thing changing is the phase shift and the sign of the amplitude. Similarly, I could have also written y equals negative 2.5 sine 4x. Sine function could have started right there. That's 1, 2, 3, negative 3 pi over 8. So plus 3 pi over 8 minus 3. Any one of those equations will give you the exact same graph. And in fact, we're going to go ahead and test that using a graphing calculator. So take out your graphing calculators. First things first, we're going to set our domain and range so we get the exact same graph. You'll notice the window settings on there are, we're going from negative pi over 4, negative 2 pi over, so negative pi over, so 1, 2, 3, 4, negative 5 pi over 8, so negative 5 pi divided by 8. To the maximum value of, we're going pi over 8, 2, 3, 4, 5, 6, 7, 8, 9 pi over 8. So 9 pi over 8. And our scale factor is pi over 4. So we'll put markers at every pi over 4. Even though it's really pi over 8, we'll put markers at pi over 4. Actually, let's put pi over 8 just to make sure that we can see that. So pi over 8. Y minimum on here that we see is 1, 2, 3, 4, 5, 6, 7, 8. So negative 8. Y maximum that we see is positive 2. And we're going to go under y equals. Make sure that you are in radian mode, or your calculator is in radian mode, because we're working with radians over here. And we're going to graph each of these equations, and hopefully, if we've done it correctly, the graph that our calculator is going to show is going to be the exact same one that we were trying to interpret. So let's start off with the first one. Y equals 2.5 sine, in brackets, 4, another set of brackets, x plus pi over 8 is a fraction, so another set of brackets, pi divided by 8, close that bracket, close the second bracket, close the third bracket. Because I'd opened up 3 brackets, I got to close 3 brackets. And then minus 3. So if I've done this correctly, and if I've come up with the equation correctly, as soon as I press graph, I should get the exact same graph as I have in front of me. Right? Let's see if that's the case. Does that match up with the graph that we have? Right, and it should. Now, here's the fun part. You can plug in any one of those 4 equations, you'll end up with the exact same graph. How will we know if we end up with the exact same graph? Well, if I plug in all those equations and I only see one graph on my screen, and that's telling me that all the graphs are exactly the same. So let me try the second equation. 2.5 sine 4 bracket x minus another bracket 3 pi divided by 8, bracket close, bracket close, bracket close, and then minus 3. Right, I'll graph it now. Again, I'll end up with an exact same graph. And in fact,